Okay, so here is a question from HCV Verma, waves chapter, and the question is regarding the speed of the wave. See, the thing is, this velocity that we have derived, or you know about it, this velocity of the wave on the string. Now, this is the velocity of this pulse relative to the string. For example, if there is a cart and in this cart is moving with velocity v, and then there is a string here, and this string which is attached to this cart, and so this string is also moving along with the cart with this velocity v. In this string with a flick, this pulse is being generated, and the tension which is maintained is T, and the mu value is depends on the string. Let's say root T by mu is 4 meter per second. Let's say this cart is moving at 10 meter per second, and so this velocity, wave velocity, which is the disturbance velocity or the shape velocity, that shape is moving along the string relative to the string with a velocity of 4. So velocity of the shape with respect to the string is equal to 4 I cap. Velocity of the string being present on the cart or this truck, that velocity of the string is 10. So overall net velocity of the shape will be equal to velocity of the shape with respect to string plus velocity of the string. So that will come out to be 14 I cap. So please do remember that whatever velocity is there, root T by mu is the velocity of the pulse within the string, or how it goes from one point of the string to the other point of the string, and that velocity is relative to the string. Okay, now coming back to this question. Now here again we have to find out the velocity of the pulse relative to the string, and there is a unique way in which this tension is maintained in the string or this rope. So you can say that this rope is quite thick, and this rope is made to undergo circular motion. See, any rope you take which is like a closed loop, and this rope which is thick and a bit heavy, what you do is you start to make it undergo circular motion or rotatory motion kind of thing. So what will happen is each part will go radially out kind of thing, and this rope will attain a circular shape, and that is what is being given, that this rope here which is quite heavy and thick, that is undergoing circular motion, or actually rotatory motion, sorry. All the particles of the rope will undergo circular motion, and this rope is undergoing rotatory motion, and for that rotatory motion of this rope, the angular velocity is omega. So if you take any small element in this rope, let's say this small element is here, and this element is subtending d theta angle at the center, this small element then will be moving in circle like this, and the angular velocity for that circular motion is omega, and the radius for that circular motion is r, which is the radius of this closed loop which is formed by rotating closed circular loop which is being formed by rotating this rope. And let's say this rope has a circular rope is forming a circular loop or radius r. Now if we take this element which is undergoing circular motion, definitely it requires centripetal force to undergo circular motion. And who provides that centripetal force? So you can say that this part of the rope is of length r d theta. Let me just write it also here. This length is r d theta. Now this r d theta element which is under consideration, it is in contact with the remaining part of the rope. So this remaining part, one is on one side which will apply a tension force tangentially, and the other is on the other side which will also apply tension force T tangentially. Because of the symmetry condition, tension is same everywhere. Okay, so now you concentrate on this r d theta element which is undergoing circular motion, and which is like experiencing this T force and T force from the either side of the rope, from either rope which are on either side of it. So if you take this r d theta element, so what we are going to do is, So half of that d theta angle will be d theta by 2. This angle is also d theta by 2. What are the two tension forces it is getting? See, the tension force is along the string, and along the string means tangential to the string. So tangential to the string means perpendicular to the radius. So one tension is T, perpendicular to the radius. Other tension is also T, perpendicular to its radius. And let's draw the tangent at the midpoint of it. So this is the tangent at the midpoint of it. And so this angle will become d theta by 2. Let me make it a bit more smaller. Oh, wait. So this will be d theta by 2, and the other angle is also d theta by 2. So you can see that this T cos d theta by 2 from the upper tension and T cos d theta by 2 from the lower tension, that will get cancelled out, and T sin d theta by 2 will get added up. So on this element as a whole, the net force is, we can say, in this way, and that is T sin component or d theta by 2, and like that there are two tensions. So this is the net force on this element, which is by the way towards its center also, because center is here. So net force towards the center is equal to mass into centripetal acceleration. So if we use that equation, because it is undergoing circular motion, so net force towards the center 2t sin d theta by 2, net force is equal to mass of this element. Mass of this element is mass per unit length into the length. So mass per unit length is mu, and length of this element is r d theta, so this is m. And what is the acceleration towards the center? Omega square r. So m into a is equal to f net. And so from here we get, see, the thing is d theta is a very small angle tending to 0. So sine of d theta by 2 will be d theta by 2. So we can write 2t d theta by 2 is mu r square omega square d theta, or T tension is equal to mu r square omega square. So this is the tension which is maintained in this rope, which is forced to do rotation motion with angular velocity omega. Now that we know the tension, if we generate a pulse, so that pulse will be traveling. So what is the travel velocity of the pulse relative to the string in which it is moving? So that velocity is root over T by mu. And how much tension are we maintaining here by rotating it with angular velocity omega? This, and divided by mu only. So what do you get is v equal to r omega. So the pulse will travel with a velocity v equal to r omega with respect to the string, or with respect to this rope. Rope point itself will have r omega velocity, and with respect to that r omega velocity, it has having a r omega velocity. So you can say that its net velocity will be either 2r omega or 0, depending on whether the pulse is moving along the velocity of the point on the string where it is present, or it is moving opposite to the velocity of the point of the string in which it is present.